Hello everyone, hope you're all safe and doing well at home. In this unprecedented time, we have to be responsible and should make use of the best available technology and hope we are doing so. And university students in the linear algebra paper, till now we have dealt with vector spaces and linear transformations, and we are remaining with a chapter to go to finish off, and the remaining chapter is rank, nullity and range of a linear transformation. In this chapter, starting with, we have two prominent definitions, and those are range space of a linear transformation and nullity of a null space of a linear transformation. And starting with the first definition, let T be a linear transformation mapped from U to V, then the range space of the transformation T is the set of all T alpha such that alpha is coming from the domain and it is denoted by R of T. You should see that again, the set of all T alpha where alpha is coming from the domain is said to be the range space of the transformation and it is denoted by R of T. And you have to note that the dimension of R of T is called the rank. The number of elements in the set R of T is said to be the rank. And as of the definition we saw before is the definition of the null space. Again, if T is a linear transformation mapped from U to V, then null space of T is the set of all alpha coming from the domain U such that T of alpha equal to 0 denoted by n of T. See that again, the set of all alpha belong to the domain U such that T of alpha equal to 0 and it is denoted by n of T. The important thing you should see here is it's not just the set T of alpha equal to 0. Here alpha is the additive identity of V, where T is mapped from U to V, so that the set alpha belongs to U such that T of alpha equal to 0, where 0 is the additive identity of V, is said to be the null space and it is denoted by n of T. And you should remember the thing that we also at some cases refer the null space as kernel of the linear transformation T. So null space or kernel, both one and the same. And as same of the dimension of R of T is rank, we have the dimension of the null space n of T is called as nullity. So the dimension is called as nullity, that is the number of elements in the set set of all alpha belong to U such that T of alpha equal to 0 is nullity. So these are the two prominent definitions we are going to play with in the further chapter. So next, after these definitions, we have four important theorems along with the very important theorem, rank nullity theorem, which is rank plus nullity equal to the dimension of the domain, which we'll see later. So first let me see which are the three theorems prior to the rank nullity theorem. Getting into the first theorem, it is as follows. If T from U to V is a linear transformation, then range space of T is a subspace of V. Given any linear transformation, its range space is always a subspace of V is to be proved. The thing. Getting into the proof, the thing is to be proved that range space, and we know that range space is nothing but the set of all T alpha such that alpha coming from the domain, given domain U. Now we have to prove this set to be a subspace of V. And recall that to prove that a non-empty subset to be a subspace of a given vector space, we need to prove two conditions. Those are, one is additive subgroup condition, that is taking any two elements and proving that the addition of two elements is also in the given set, non-empty set. And the other is the scalar multiplication, taking a scalar from the field and an element from the non-empty subset, proving that the scalar multiplication of those two is in the same set. In the right way, we will prove that, and also clearly observe that the given set, the set we have R of T is clearly a non-empty subset. So I will take any two elements, say beta 1 and beta 2 in R of T, which is to be proved as a subspace. So if I consider beta 1 and beta 2 to be any two elements in R of T, there always exists alpha 1 and alpha 2, two elements in U such that T of alpha 1 is beta 1 and T of alpha 2 is beta 2. If I am taking any two elements, that's the definition of range space, R of T, is it? So beta 1 and beta 2 are two elements from range space. Then there must exist two elements alpha 1 and alpha 2 in U such that T of alpha 1 is equal to beta 1 and T of alpha 2 equal to beta 2. Now I will add these two elements, say beta 1 plus beta 2, which is nothing but T of alpha 1 plus T of alpha 2. Since given that T is a linear transformation, T of alpha 1 plus T of alpha 2 is same as T of alpha 1 plus alpha 2. And you have to see that this is nothing but in the form of T of alpha. So this is an element of range space. T of alpha 1 plus alpha 2 is an element of range space. So since this is equal to this, we clearly have this implies beta 1 plus beta 2 belongs to the range space. So taking any two elements and adding them, we showed that though again the resulting element is in the non-empty subset R of T. Similarly, the next step is to prove that taking a scalar from the given field F and an element beta, say beta in R of T, I need to prove the scalar multiplication is also in the non-empty subset. So doing that, C into beta is nothing but C into, say beta is equal to some T of alpha. And again, since given that T is a linear transformation, C into T of alpha is same as T of C alpha. And again, this is an element of the form T of alpha which will be present in the set R of T. So again, what will be proved that C of beta belongs to R of T. So these two conditions imply that the range space of T is a subspace of V. Similarly, we have the other theorem, and that theorem states that if T from U to V is a linear transformation, then null space of T is a subspace of U. The theorem is the null space of T is a subspace of domain. So range space is a subspace of codomain and a null space is a subspace of domain. On the same lines, you can prove the theorem, and so we will not get into the theorem and we will move on to the next. Moving on to the next theorem, we have again T to be a linear transformation mapped from U to V. Then the thing is to be proved is T is 1 to 1 if and only if n of T equal to 0, where 0 is the zero vector of domain U. So now the thing is to be proved in either way because we have if and only if condition. So for first I will assume that T to be 1 1. Now I should arrive at n of T equal to 0. So I will consider an element, say alpha, in n of T. Since alpha is in null space n of T, alpha must be mapped to 0 element. So this implies T of alpha equal to 0. And we know that 0 elements are mapped to 0 elements under linear transformation. So this implies T of alpha equal to T of 0. And what can you think next? Since our assumption is 1 to 1, T of alpha equal to T of 0 implies alpha equal to 0. I took alpha to be in n of T and I showed that alpha is 0. Therefore, I will conclude that n of T must be singleton 0. So assuming that T is 1 to 1, I proved n of T is 0. So the one way is proved now. Now I will assume the reverse way, that is n of T equal to 0. I will assume that n of T equal to singleton 0 and I will arrive at T is 1 to 1. And the general method to prove that mapping is 1 to 1 is we will consider two elements and consider T of alpha equal to T of beta and showing that alpha equal to beta. So now I will consider T of alpha equal to T of beta for any two elements, say alpha and beta, coming from the domain. Now I should arrive at alpha equal to beta and we are done with the theorem. So if T of alpha equal to T of beta, this implies T of alpha minus T of beta equal to 0. And since given that T is a linear transformation, T of alpha minus T of beta is same as T of alpha minus beta, and that is equal to 0. The next thing is, since T of alpha minus beta equal to 0 and T of alpha minus beta equal to 0, therefore alpha minus beta should be in null of T. T of alpha minus beta is 0 implies alpha minus beta is mapped to 0 element, and alpha minus beta, that implies alpha minus beta should be in null space, therefore alpha minus beta is in null space, and our assumption is n of t is 0, therefore this must imply alpha minus beta equal to 0, and this implies alpha equal to beta. So I took T of alpha to be equal to T of beta, and I arrived at alpha equal to beta, which proves T is 1, 1. So in the second case, case we assumed n of t to be 0, and I arrived at T is 1, 1, which proves both sides of the theorem. So coming on to the most important theorem, rank nullity theorem, and it states as follows. If T from U to V is a linear transformation, then rank plus nullity equal to dimension of U, which is nothing but dimension of domain. So rank nullity theorem states that rank plus nullity is dimension of domain. Coming to the proof, if I consider P to be the set of all alpha 1, alpha 2 and so on up to alpha m to be the basis of null space, to be the basis of null space. I took P to be the basis of n of t, and you know that dimension of n of t is nothing but nullity, and dimension of n of t is here is nothing but the number of elements present in the basis of the null space. So here the number of elements present in that basis is m, so I came at nullity to be equal to m. Now we have dimension of n of t to be m, and we have this to be the basis of null space, and extending this we can also have this to be a basis of the dimension u, in the sense if I consider Q to be the set alpha 1, alpha 2 and so on up to alpha m, and adding some more elements, say n number of elements, let it be beta 1, beta 2 and beta n, I can have this to be the basis of dimension u. So extension of the basis of null space serves as a basis to the dimension of the domain. So I can claim this to be the dimension of domain. So let Q to be the basis of U. So now it is the basis of U, therefore I can say dimension of U to be the number of elements present in the basis of U, that is nothing but m number of alphas plus n number of betas. So I have dimension of U to be m plus n. But already we came at dimension of null space to be m, which is nothing but nullity. So in place of m here, I can replace it by nullity. So I have now dimension of U to be equal to nullity plus n. What to be proven? Rank plus nullity equal to dimension of U. So we have nullity plus n. So now the problem reduces to show that n equal to the rank of T, rank of the linear transformation. We came at dimension of U to be nullity plus n. The thing is to be proved rank plus nullity equal to dimension of U. So we are remaining with to prove that n is same as rank of, n is nothing but the rank of T. In order to prove that n to be the rank of T of the linear transformation, I need to prove that T of alpha 1, T of beta 1, T of beta 2 and so on up to T of beta n is basis of R of T, isn't it? Since if I prove that this is a basis of R of T, then dimension of R of T is nothing but the rank, then dimension of R of T is nothing but the number of elements in the basis of it. So the number of elements in the basis of R of t here is n. So if this is a basis of R of t, then definitely the rank will be equal to the dimension of R of t, that is nothing but n. So it is crucial in proving rank to be n, we have to prove that this is to be a basis of R of t. In order to prove that this is a basis of R of t, again we need to prove two things in order to a non-empty set to be a basis, isn't it? So first, this should span R of t. Spans in the sense, if I take any element in R of t, it must be expressed as a linear combination of those elements. And the second thing is, this set should be linearly independent. So proving this to be a basis of R of t is nothing but to prove this spans R of t and this set is linearly independent. First, we shall prove that this set spans R of t. In order to prove that this set spans R of t, I will take an element beta in R of t. So this implies there exists alpha in the domain U such that t of alpha equal to beta. I took an element beta in R of t, and that implies there must exist an element alpha in the domain such that t of alpha equal to beta. And since alpha is in U and Q is a basis for U, I can express alpha as the linear combination of some elements. How do you have some elements in the basis? How do you have the basis of U? It was alpha 1, alpha 2 and so on up to alpha m, and beta 1, beta 2 up to so on beta m. So now I can express alpha as a linear combination of am into a1 into alpha 1 plus a2 into alpha 2 and so on up to am alpha m. Likewise, say some b1 into beta 1 and so on up to bn times beta n. So now I have alpha to be a linear combination of such elements, and consider that t of alpha equal to beta. Beta equal to t of alpha. Now alpha is this, so substitute these things in place of alpha. And since you know that t is a linear transformation, this is same as t of a1 alpha 1, t of am alpha m, t of b1 beta 1 and so on, t of bn beta n. This is again a linear transformation. This is same as a1 times t of alpha 1 and so on plus am times t of alpha m plus b1 times t of beta 1 and so on up to bn times t of beta n. And you know that since alpha 1, alpha 2 and so on up to alpha m forms a basis for null space, they are all equal to 0. That is, alpha 1, alpha 2 and so on up to alpha m all are equal to 0 because alpha 1, alpha 2 and alpha m, those set forms a basis for null space. So they are all equal to 0. So these things will be 0, and now we are remaining with beta to be equal to b1 times t of beta 1 plus b2 times t of beta 2 plus b3 times and so on up to bn times t of beta n. So now I am able to express beta as a linear combination of the elements of their basis dimension of U. So beta, that is this set t of beta 1, t of beta 2 and so on up to t of beta n spans R of t. Now the only thing left to prove is to show that the set t of beta 1, t of beta 2 and so on t of beta n is linearly independent. So I will consider the linear combination of these elements and I will equate it to 0. Since t is a linear transformation, this is same as t of c1 beta 1 C2 beta 2 and so on up to n beta n. Again, since T is a linear transformation, I can write this as and since this is mapped to 0, this signs that this must be in null space, isn't it? T of alpha equal to 0, so this must be in null space. Now this implies, as we have P to be the basis for null space, if you remember that P is a basis for null space, where P is alpha 1, alpha 2 and so on up to alpha m, we should have C1 beta 1 plus C2 beta 2 plus Cn beta n plus so on up to Cn beta n to be equal to, say, some linear combination d1 alpha 1 plus d2 alpha 2 plus so on up to dn alpha n, because alpha 1 alpha 2 and so on up to alpha n, that set is basis for null space, so we should have this, and this implies C1 beta 1 plus C2 beta 2 plus Cn beta n minus d1 alpha 1 minus d2 alpha 2 and so on up to dn alpha n must be equal to 0. This is possible if and only if all the scalars equal to 0. So this is possible if and only if all the scalars are 0, and since all the scalars are 0, we proved that this set is linearly independent, and previously we have proved that this set spans R of t, and now we have proved this is linearly independent. So together that implies that R of t is the dimension, the basis for R of t is nothing but this. So the dimension of this basis is n, so the rank must be equal to n, and hence rank plus nullity equal to dimension of U, which is nothing but domain. Next, we have some set of problems relating to rank and nullity. So given verify rank nullity theorem for the matrix A to B 132 minus 172 101. First, we will find the rank of the given matrix. In order to find the rank of the given matrix, we will follow the method of elementary row operations, and the left topmost corner is 1, and the thing is to do this element as 0 in order to find the rank. So following the row operations in R2, I will add R2 and R1 so that will be 0, and for R3 I will do R3 minus R1. So the operations are R2 plus R1 and R3 minus R1, which yields a matrix such that R2 plus R1 minus 1 0 7 3 10 2 2 4, and 1 minus 1 is 0 minus 3 and minus 1. If you observe, we cannot do any further elementary operations, so this is the reduced matrix, say A. So therefore the rank of A is 3. We cannot do any further operations, so we got that rank to be 3. And nullity, we will take n of t, which is nothing but p of x, y, z to be 0, since this is a 3 cross 3 matrix. And to find the linear transformation, this is nothing but t of x minus y plus z comma 3x plus 7y comma 2x plus 2y plus z equal to 0. So this is the equation. Now in equating each coordinate to be equal to 0, we have and 2x plus 2y plus z to be equal to 0, call them as set of equations 1, 2 and 3. Now it's easy to see that if we operate 1 and 3, z and z gets cancelled. So from 1 and 3 I have x minus y plus z equal to 0 and 2x plus 2y plus z equal to 0. So this straightly implies that minus x minus 3y equal to 0. Let me call this as equation 3 and equation 4. Now if you check 2 with 4, 3x plus 2y equal to 0 is the equation 2, and equation 4 minus x minus 3y is 0. This will be 3x plus 2y equal to 0 and minus 3x minus 9y is 0, and this is nothing but 7y is 0. This implies y equal to 0, and substituting y equal to 0 in equation 2, we also get x to be equal to 0. Again, substituting x and y to be 0 in equation 3, we get z to be equal to 0. Since x, y and z all are 0, that implies t of x, y, z equal to 0. N of t is nothing but 0, 0, 0. So there is nothing but 0th coordinate in 3-dimensional space. So dimension of n of t is nothing but 0, that is nullity is 0. So verify rank nullity theorem was the question. We got rank to be 3 and nullity to be 0. So 3 plus 0 is 3, which is nothing but the dimension of the matrix, which implies the dimension of the rank matrix of the linear transformation. And we have the same kind of problem. T of given rank verify rank nullity theorem for t of xy equal to x plus y comma x. In the previous kind we had a matrix, so we have one more step to do in this problem. So given that linear transformation is from R2 to R2, we will consider the standard basis for R2, which is nothing but t of 1, 0 and 0, 1. If you find t of 1, 0, it is x, that is 1 x plus y, and it is x, so this is 1 comma 1, and t of 0, 1 is again it is 1 and this it is 0. So the matrix associated with it, say A, is 1, 1 and 1, 0. Now if I apply elementary transformation for this, in order to make this as 0, it is R2 minus R1. I will be having A to be equal to 1, but this will be minus 1. So anyhow, we have rank of A to be 2. Now in order to find the nullity, we have t of xy to be equal to 0, and t of xy is nothing but x plus y equal to 0 and x equal to 0. Since x equal to 0, x plus y equal to 0, we have x to be equal to 0 to be equal to y. Again, we have dimension of n of t to be equal to 0. Nullity is null space is nothing but 0 comma 0. So we have dimension of null space to be 0, that is nullity. So we have rank to be 2, nullity to be 0. 2 plus 0 is nothing but 2, which is the dimension of the matrix associated with the linear transformation. This verifies rank nullity theorem for this. So next problem is about to find all the parameters in the rank nullity theorem. So the problem is to find range, kernel, rank and nullity of the linear transformation t from R3 to R3 defined by t of x, y, z equal to x plus y, x minus y and 2x plus z. First, we will try to find the rank. In order to find the rank, we have to find the matrix associated with it. Again, as this is a mapping from R3 to R3, we will consider the standard basis for the linear transformation, which is as follows. So substituting x to be equal to 1, we get this as 1, and again this is equal to 1, and this is equal to 2, and y to be equal to 1, this is 1, and this is minus 1, and this is 0, and this is z equal to 1, this is 0, 0, and this is 1. So this implies if there is a matrix say A, then that also associated matrix with the linear transformation is 1, 1, 2, 1, minus 1, 0, 0, 0, 1. Now in order to find the rank of the matrix, we will apply the linear row elementary form. R2 minus R1 yields us is 1, 1, 2, and this is 0, minus 1, this one is minus 2, this is minus 2, and this will be 0, 0, 1. And clearly if you observe that we cannot do any further operations in order to make this as 0, so rank remains to be 3. So rank of A is 3, as this cannot be done further equated to 0, so rank of A remains to be 3. Now range, we will consider this to be equal to set of all x times 1, 1, 2 plus y times 0 minus 2 minus 2 plus z times 0, 0, and this is nothing but the set x plus 0 plus 0, this is x, and this is x minus 2y plus 0, so this is x minus 2y, and this is 2x minus 2y plus z, 2x minus 2y plus z. Here this set is such that x, y and z are real numbers. So now we have found the range. Now nullity, which is nothing but n of t, we do that t of x, y, z to be equal to 0, and if we equate this to be 0, which is nothing but x plus y, x minus y, 2x plus z equal to 0, we arrive at 3 set of linear equations. X minus y equal to 0, 2x plus z equal to 0, and solving 1 and 2, we get 2x 0, so x to be equal to 0, and substituting in either of 1 and 2, we get y to be equal to 0, and therefore in substituting the equation 3, we get z to be also equal to 0. Therefore all x, y, z's are 0, n of t should be 0, therefore nullity is 0, and we got in the previous case rank to be 3, and here nullity is 0, rank plus nullity is equal to dimension of domain, and we have find what is range. This completes the problem.